In this video, we're going to think about some really basic things that we do with fractions. The goal in the end is to do operations with fractions involving algebraic expressions, but for starters, we're just going to look at what happens when you add and multiply regular old fractions with numbers. So one thing that you probably remember is that it's a little bit hard to somehow combine fourths and sixths unless you think about it really carefully. So we tend, when we see things like 3/4 plus 5/6, to give those things the same denominator. So one way that people tend to do that is they'll say, well, you got to turn fourths and sixths into 20/4. And the reason they might choose 20/4 is you could say like, well, we're going to multiply by 6/6 over here, and we're going to multiply by 4/4 over here. In other words, just multiply those two denominators together, and that's certainly fine. So what do you end up with if you do that? You get 3 times 6 is 18, plus 5 times 4 is 20, divided by 24. And of course, that gives you then 38 over 24, which you can reduce. I mean, you can divide 38 by 2, so that's going to be 19 over 12. So that's certainly one way to approach this. There's another thing that you could do that saves just a little bit of effort. If you look at fourths and sixths as being the denominators, you realize, well, 4 is 2 times 2, and 6 is equal to 3 times 2. So what denominator could you use that contains all the factors that you see there? Well, you could use 12, because 12 is equal to 2 times 2 times 3. That's the prime factorization of 12, so it contains enough 2's and enough 3's to capture both 4 and 6. So instead of 3/4 plus 5/6, we're going to think of it as 3/4, and then we're going to multiply by, let's say, 3/3, and then we'll do 5/6, and we're going to multiply by 2/2. And that gives us then 9/12 plus 10/12, which is exactly 19/12. So the point is, before we just kind of plunge ahead, you can think a little bit more about a smaller common denominator, the least common denominator, and that saves just a little bit of effort in the end. Now we're going to multiply these two fractions. And of course, you may remember that when you multiply fractions, you can just multiply the numerators and multiply the denominators. So 3 times 5 is 15, 4 times 6 is 24, and so this is going to be 15/24. Of course, that reduces, right, because 15 and 24 are both divisible by 3, and so you could make this 5/8. And that's certainly a perfectly fine way to do it. I'd like to hope you think that it's maybe a little bit less work if you start by saying, well, what is this really? It's 3 over 4 times 5 over 2 times 3. And then when you actually go and do 3 times 5 over 4 times 2 times 3, you can cancel the 3's. And so you're really left then with just 5 over 8. So somehow you can sort of see right at the beginning that this 6 is really 2 times 3, and so you can cancel those two 3's. Now we're going to do some adding and eventually multiplying of fractions, but we're not using numbers anymore. We're using algebraic expressions. And in some ways, the most general thing that you might have is something that looks like a over b plus c over d. And the way to handle that is pretty much the same thing we did a few minutes ago. So you can think of taking a over b plus c over d and giving them the same denominator. In other words, you might put a denominator of bd on the left fraction, but that means you really need to multiply by d on the top as well. And then on the right fraction, you would need to multiply by b over b so that you still have a denominator of db. And then this is, of course, going to turn into AD plus BC divided by BD. So that's the sort of most general thing that you could do. You can do that very same thing with this slightly more complicated looking, but ultimately more or less the same kind of problem here. We can take 3x over x squared plus x, and we can give it the same, or we can give it a denominator that's going to be the product of these two denominators. So what we'll do is we'll multiply by x squared minus 1 down here, and we better also multiply by x squared minus 1 up there. And then we have 5 over x squared minus 1, but of course we're going to need to give it the same denominator, so we might put an x squared plus x down here, and similarly an x squared plus x up there. And that's perfectly reasonable, and of course in the end, what do we get? We're going to distribute the 3x through those parentheses and the 5 through those parentheses, and that should give you 3x cubed minus 3x, and then we're going to have plus 5x squared plus 5x, and that's all over x squared plus x times x squared minus 1. And again, the reason we could do that is once we had the same denominators, we could just add the numerators. So that's one approach to doing this. But again, I hope I can convince you that there's maybe a different approach that takes just a little bit less computation, or at least gives you an answer that looks a little bit nicer. So here's what we're going to do. Before we ever add these things together, before we ever even get a common denominator, we're going to notice that x squared plus x is really x times x plus 1. And similarly, x squared minus 1, that's really x minus 1 times x plus 1. So before we get really carried away with our denominator, we can say, well, we really don't need the whole product of those two things. All we need is to introduce this factor of x minus 1 over on the left fraction. And then similarly, we need to introduce this factor of x over on the right fraction. So what we're going to do is we're going to write 3x over, and I'm going to actually call this x times x plus 1. And then I'm going to introduce that factor of x minus 1 here and here. And then the second fraction, 5 over, and again, I could call it x squared minus 1, but I'm going to call it x plus 1 times x minus 1. How do I give that the same denominator? I introduce this factor of x on the bottom, and then I better introduce that same factor on the top. And now these two fractions have the same denominator, and this allows me to just add the numerators. So what do I get here? I get 3x squared minus 3x, so that's from doing these two. And then I get plus 5x, all divided by x times x plus 1 times x minus 1. And of course, this simplifies to 3x squared plus 2x divided by that same denominator. So we saved a little bit of computation, and we made our answer just a little bit easier to deal with in the end when we thought ahead before getting a common denominator. Same kind of thing works when you're multiplying fractions. If you don't think ahead, you can do something that's perfectly legal, but maybe makes your answer a little more complicated. So you can distribute all these various things on the numerator, and so you're going to end up with x squared times x squared, that's x to the fourth. Then you're going to have 9x squared. Then you're going to have x cubed. And then finally a 9x that comes from those guys. And then in the denominator, you're going to have 3x to the third. That comes from that computation, that product. And then you're going to have minus 3x. And then you're going to have plus 7x squared. And then finally minus 7. And this is a correct answer, but it's a kind of correct answer that's kind of complicated looking. So let's hope we can do a little better. And the thing that we can do that's better is to realize that right off the bat, we have x times x plus 1 over 3x plus 7 times x squared plus 9 over x minus 1 times x plus 1. And what can we do? Well, you could multiply the numerators and multiply the denominators, but I hope you'd see that when you do that, you're going to get this factor of x plus 1 in both the numerator and the denominator. So before I actually bother, I'm going to cancel those two things. And then what are we left with? We're left with x times x squared plus 9 divided by 3x plus 7 times x minus 1. And for the most part, it's actually a little bit easier. You actually know more about your algebraic expression if you leave it like this in the most factored form possible, rather than doing something like x cubed plus 9x over whatever you get down there. So we're going to leave it just like this. This is just a quick reminder that when you divide fractions, you multiply by a reciprocal. So for instance, if you have a over b divided by c over d, you ultimately end up just doing a over b times d over c. So you would get a times d divided by b times c. In this expression that you see right here, it might look like it's really different, but in some ways it's actually exactly the same. In fact, well, even easier in some ways, it's a over b divided by c over 1. So in other words, we could think of this h as being h over 1. And what happens when we think of it that way? Well, we can do the exact same thing we did a minute ago, which is to say, okay, this is 6xh plus h divided by x times x plus 1. So there's your a over b part, and then we have to multiply by the reciprocal of the bottom, so that's 1 over h. And so this ends up being 6xh plus h divided by x times x plus 1 times h. And this is, again, certainly a right answer. Like a lot of situations, though, it can be made even better. Couple of things. One thing that I hope you kind of notice here is that when you divide by this h, really all that ends up happening is this h moves up next to the denominator of the numerator. So that's where this h ended up going. So ideally, you get to the point where in the end you see something like this, and then you can just quickly say, oh, it's going to be the fraction that you see up in the top divided by h times x plus 1. Furthermore, you can factor an h out of the top, and then this becomes something that simplifies even a tiny bit more. You can cancel these two h's, and then you're left with 6x plus 1 divided by x times x plus 1. So this is an example of something you want to try to avoid. If you do something like this, you would get put in mathematics jail and locked up for many years. So what's the problem here? Well, we certainly know things like 3 plus 2 over 7 is equal to 3 over 7 plus 2 over 7. That's just how addition of fractions works. But it's important to realize that only works that way if you've got the same denominator and then you're combining the numerators. That's not what this mistaken student did up here, right? You can't do that when you have two different denominators. You can't add the denominators and keep the numerator the same. So if anything, if you saw this expression right here, what, if anything, could you do to it? Well, you could do A over B times C over C plus A over C times B over B. And so this would then become AC plus AB over BC. And if you wanted, you could factor the A out of the top, so it would be A times C plus B over BC. So here's one other example of a kind of thing that I will occasionally see students do, is they'll take an expression like what's written there, and they'll do some sort of weird canceling. They'll write stuff like that and say this is either equal to B or this is equal to 1 plus B. And neither of those is okay to do. So what, if anything, can you do? Well, you can take advantage of the idea that if you have something like, 2/7 plus 3/7, that's equal to 2 plus 3 over 7. But it actually works both ways. So in other words, if you had like 2 plus 3 over 7, you can split that into 2/7 plus 3/7. And that's kind of the helpful way to think about that, because then when we have this expression here, we can say, well, that's really equal to A over A plus B over A. So this is really equal to, A over A is just 1. And then B over A, there's nothing you can do to that, so you can just write it as B over A. So what do you get when you simplify this? You get 1 plus B over A. You don't get 1 plus B. So again, there's no kind of strange canceling you can do right there. The best you can do is you can split it into two fractions like we did here, and then realize that that first fraction ends up being 1. But the difference is that you get this denominator of A over here.